Let's look at a cubed over b squared times b over a squared. We want to write these in expanded form. A cubed is a times a times a, then times b. That's what we would have across the top. And then on the bottom, b squared is b times b. We would multiply that by a squared, which is a times a. Cancel what can cancel. Two a's on the top with two a's on the bottom. One b on the top with one b on the bottom. That leaves us with a over b. We can use this methodology to evaluate fractions raised to powers. 3/4 cubed means 3/4 times 3/4 times 3/4. But that's the same as 3 times 3 times 3 over 4 times 4 times 4. Nothing cancels. 3 times 3 is 9, times 3 is 27. 4 times 4 is 16, times 4 is 64. It does not reduce. So just like we wrote a cubed, for instance, as a times a times a, 3/4 cubed is 3/4 times 3/4 times 3/4. -4/5 squared, with the negative inside of parentheses being affected by the square, would be -4/5 times -4/5. Negative times negative is positive. 4 times 4 is 16. 5 times 5 is 25. Positive 16 over 25. Now, it's natural that when we're talking about multiplication, that we know division is in the distance. It's coming up soon. And we can't talk about division without talking about something called the reciprocal. Reciprocals are two numbers whose product is 1. In other words, 9/10 times 10/9 equals 1. So 9/10 and 10/9 are reciprocals. Why does it equal 1? Because 9 times 10 is 90. 10 times 9 is 90. 90 over itself equals 1. So to find the reciprocal of a fraction, we just switch the numerator and the denominator. For 9/10, it became 10/9. Just flip it. 1/11 becomes 11 over 1. Just flip it. And 11 over 1 would be 11. So let's find these reciprocals. The reciprocal of 4/9 would be 9/4. Flip the top and bottom. The reciprocal of 13/9 would be 9/13. Flip the top and the bottom. The reciprocal of 9 over 1 would be 1 over 9. Flip the top and the bottom. Okay, now we know what a reciprocal is. Now we can talk about dividing fractions. To divide two fractions, we multiply the first fraction by the reciprocal of the second fraction. So if A, B, C, and D are numbers, and B, C, and D are not 0 because they're going to end up on the bottom of a fraction at some point, and we can't divide by 0. A over B divided by C over D would be A over B times D over C, which is A times D over B times C. In other words, we keep the first fraction. We change division to multiplication. We flip the second fraction. Multiply by the reciprocal is division. Keep, change, flip. Keep, change, flip. Or if you want to say keep, flip, change, then you've got yourself a chicken place.
Well, in order to divide two fractions, let's say we had a over b, some random fraction, divided by c over d, we leave the first fraction as it is, we change division to multiplication, and we take the reciprocal of the second. We keep the first, we change division to multiplication, and then we flip the second. And if you want to say keep, flip, change, then you have the kernel to help you out. But dividing by a fraction is multiplying by the reciprocal. Division is just multiplication of an amended problem. Keep in mind, canceling is something that is exclusive to multiplication. So you never cancel a division problem until it appears as a multiplication problem. So we would not cancel 9 and 33 because they both divide by 3, because what we see is a division problem, not multiplication. How do we handle this? Keep the first. Flip the second. Change division to multiplication. And then it's just more of what we did in the first half of class. 33 and 11 are both divisible by 11. 33 divided by 11 is 3. 11 divided by 11 is 1. 9 times 3 is 27. 1 times 4 is 4. No need to change it to a mixed number. This would be 27 over 4. Let's do another. 5/6 divided by 1/7. Keep, flip, change division to multiplication. 5 times 7 is 35. 6 times 1 is 6. 35 over 6. See, once we learn this one new thing, we just added on to what we already knew. 2/7 divided by 3/4. Keep, flip, change division to multiplication. Nothing cancels. 2 times 4 is 8. 7 times 3 is 21. 8 21sts. Do not cancel the 2 and the 4 because that's a division problem. No cancellation can happen until we have a multiplication problem. Next, let's take a look at 5/11 divided by 7/11. Keep, flip, change division to multiplication. The 11s cancel, 1 over 1. 5 times 1 is 5. 1 times 7 is 7. 5 sevenths. Am I trying to trick you with this next one? Maybe. But you're not going to fall for it. You're smarter than that. 9/8 divided by 8/9. No, this is not 1 because we cannot cancel those 8s and we cannot cancel those 9s. Why can't we cancel them? That's right, because it's a division problem. We divide by keeping the first, changing division to multiplication, and flipping the second. 9 times 9 is 81. 8 times 8 is 64. 81 over 64. Dare I say these are kind of fun. 5/9 divided by 5/3. Keep, change, flip. Once we have multiplication, we can cancel 5 over 5. That's 1 over 1. 3 over 9, that's 1/3. 3 divided by 3 is 1. 9 divided by 3 is 3. 1 times 1 is 1. 3 times 1 is 3. Another one. Why not? You asked nicely. 12/5 divided by 7/5. Keep, change, flip. 5 over 5 cancels. 1 over 1. 12 times 1 is 12. 1 times 7 is 7. 12 sevenths. Let's get these a little more interesting, shall we? One-fourth. One-fourth divided by 11/6. Keep, change, flip. Some canceling. 6 and 4 can both be divided by 2. 3 and 2. 1 times 3 is 3. 2 times 11 is 22. 3 over 22. Okay, it was a little more exciting. What can I say? It's only division of fractions. The bar can only be set so high. 4/59 divided by 1/6. Keep, change, flip. Nothing cancels. 59 isn't divisible by 2 or 3 or 6. So multiply across the top. 4 times 6 is 24. On the bottom, 59 times 1 is 59. 24/59. Let's look at 4 over 33 divided by 20 over 143. Let's start, as always, with keep, change, flip. And these numbers are very large. We can start by Canceling the 4 and the 20. Both are divisible by 4. 4 divided by 4 is 1. 20 divided by 4 is 5. And at this point, I wouldn't blame you if you didn't think there was anything else to cancel. You would do 1 times 143 is whatever. 33 times 5 is whatever. And then you would need to start reducing. But let's take a look at the 143 and the 33, because they do have something in common. It's not going to be 3. 143 is not divisible by 3, because 1 plus 4 is 5 plus 3 is 8. The digits don't add up to a multiple of 3. But 33, what's the other obvious thing it's divisible by besides 3? 3 times what is 33? 11. 143 is actually 13 times 11. How did I recognize that? There's a divisibility test for 11. Anything times 11, you actually add the digits together. 1 times 3 is 4, and stick it in between. So 11 times 13, 1 plus 3 is 4. 11 times 13 is 143. So I recognize that's a 4 in between 1 and 3. That makes this divisible by 11. 143 divided by 11 is 13. 33 divided by 11 is 3. 1 times 13 is 13. 3 times 5 is 15. 13 fifteenths. Let's use this 11 trick again real quick. What's 15 times 11 going to be? 1 plus 5 is 6. 15 times 11 would be 165. What about 23 times 11? 2 plus 3 is 5. 253. What about 21 times 11? 2 plus 1 is 3. So that's a nifty little times 11 trick that helped us out here. Got us to 13 over 15 a little bit easier than reducing larger numbers. Speaking of 11, we got a lot of them in this problem. 10 elevenths divided by 10 elevenths. Well, I'm going to come back to the shortcut in a second, not the 11 shortcut. This is a completely different thing. But if we did this with keep, change, flip, the 10s cancel 1 over 1, the 11s cancel 1 over 1. Our answer is just 1. Anything divided by itself is 1. Remember, 5 over 5 is 1. Anything divided by itself, 10 elevenths divided by itself is still going to work out to 1. And that's because keep, change, flip. That'll give us a little bit more work. When we first did division, recall that 0 divided by anything was 0. 0 divided by anything is 0. 0's on the top, we get 0. But anything divided by 0 or 0 on the bottom was undefined. So in this next example, when we have 2/9 divided by 0. As soon as we see divided by 0, our answer is undefined. But the 0 coming first, 0 divided by, say, 15/7, the 0 coming first is okay. It just means we have an answer of 0. Why? Keep, change, flip, 0 times anything is 0. When 0 comes second, we can't flip 0, so we can't do it. Okay, let's work on a larger problem. 16/105 divided by 64/175. So how do we start? It won't be canceling because it's a division problem. But we turn division problems into multiplication. Keep, change, flip. The problem we're actually going to be working on is 16/105 times 175/64. I'm going to work on canceling, and I'm going to use small numbers. I know I can do 4, but I'm going to just, they're both even. I'm going to break them down by 2. 16 and 64 broken down by 2 would be 8/32. Still even, cut them in half again, 4/16. Still even, cut them in half again, 2/8. Still even, cut them in half again, 1/4. So it doesn't matter if you didn't realize that you could divide them both by 16, or that you can divide them both by 8, or you can divide them both by 4. You can just keep going by 2. There's no end to the number of times you're allowed to cancel. Let's do the same over here. 105 and 75. They both end in 5. So what are we going to divide by? 5. I'm going to need some help, though. $175 divided by 5. 5 goes into 17 3 times. 5 goes into 25 5 times. So 75 divided by 5 is 35. 175 divided by 5 is 35. I think I said that wrong. How about 105 divided by 5? If we do that, we're going to get 21. And then 21 and 35, we can divide them both by 7. 35 divided by 7 is 5. 21 divided by 7 is 3. So what do we have here? We have 1 times 5 is 5 over 3 times 4 is 12. 5/12. Palate cleanser. Those were big numbers. Let's bring it back to something a little more comfortable. 1/6 and divided by 5/3. Keep. Change division to multiplication. Flip the second fraction. We can cancel 3 and 6, both divisible by 3. 3 over 6 is 1 over 2. So 1/10. Let's go ahead. There'll be more practice with this in the homework. But let's go ahead and bring in dividing by whole numbers. 5/12 divided by 15. So remember, when we were doing our multiplication problems and we had a whole number pop up, we had to write it as itself over 1. We have to see it as a fraction before we can flip the fraction. Keep the 5/12, change division to multiplication, and flip the 15 over 1. 1/15. 5 and 15 can both be divided by 5. So 1 over 3. 1 times 1 is 1. 12 times 3, 36. So 1 over 36. What about if the whole number comes first? That's okay. If we have 6 divided by 7/10, we would rewrite 6 as 6 over 1. And then keep, change, flip. 60 over 7. And unless they give us an indication that we need a mixed number, since it's not containing a mixed number in the original problem, we do not need to divide that out and get a mixed number.
Let's introduce some variables into this. 3y divided by 4 divided by 5y cubed, or the fraction 3y over 4 divided by 5y cubed. Well, there's a division problem. We can write 5y cubed as a fraction by putting it over 1. Anything over 1 is itself, so anything can be written as a fraction by putting it over 1. And then we'll keep, change, flip. Keep the 3y over 4, change division to multiplication, flip 5y cubed over 1 so that it's 1 over 5y cubed. 5y cubed is 5 times y times y times y. It's not 5y times 5y times 5y because there was no parentheses there. The 5 is not involved with the cubed at all. It's 5 times y cubed. 5 times y times y times y. The y on top cancels with one of the y's on the bottom. We're left with 3 times 1 is 3 over 4 times 5 times y times y. 4 times 5 is 20. Y times y is y squared. 20y squared on the bottom. An evaluate problem. We haven't had one of these in a while. If x equals 7/8 and y equals -1/3, A, evaluate xy, x times y, and B, evaluate x divided by y. So we can see A is already started. Plug it in, plug it in. Replace x with 7/8. Replace y with -1/3. Positive times negative is negative. 7 times 1 is 7. 8 times 3 is 24. -7/24. B, divide x by y. Plug it in, plug it in. 7/8 divided by -1/3. Keep, change, flip. 7/8 times -3/1. Positive times negative is negative. 7 times 3 is 21. 8 times 1 is 8. -21/8. Cedar Point is an amusement park located in Sandusky, Ohio. Its collection of 72 rides is the largest in the world. Of the rides, 2/9 are roller coasters. How many roller coasters are in Cedar Point's collection of rides? Doesn't it feel like more than 2/9 of the rides in Cedar Point should be roller coasters? How many rides do they actually have? I guess the answer to that is 72. So, how many roller coasters are at Cedar Point if 2/9 of the 72 are roller coasters? So, remember our list of keywords. Of was a multiplication word. 2/9 of 72 means that we have 2/9 times 72. So let's solve 2/9 times 72. 72, recall, would be 72/1 as a fraction. Once we have 72/1, we can multiply across the top and multiply across the bottom. 2 times 72 over 9 times 1. We can simplify a little bit. 72 is 9 times 8. So if we write it as 9 times 8, that 9 on the top will cancel with the 9 on the bottom, leaving us with 2 times 8 over 1, which is 16/1, which is just 16. So the number of roller coasters at Cedar Point is 16, at least at the time that this was made. This being the slide, the problem, not the video. And that is it for this topic. The topic is adding and subtracting like fractions, least common denominators, and equivalent fractions. The objectives in this topic: add or subtract like fractions, add or subtract given fractional replacement values, solve applications by adding or subtracting like fractions, find the least common denominator of a list of fractions, and write equivalent fractions. Fractions with the same denominator are called like fractions, very similar to how fractions or expressions that had the same variables, terms with the same variables, were called like terms. So just like 2x and 3x would be like terms, 2/5 and 3/5 would be like fractions. They have the same denominator. And just like 2x and 3y were unlike terms, 2/5 and 3/4 would be unlike fractions. They have different denominators. So I mentioned previously that multiplication was the nice one. Multiplication was the one that worked the way you would expect it to. Multiply the numerators, multiply the denominators, and you get your multiplied product with fractions. Adding does not work like that. We do not add across the top and add across the bottom. For instance, A over B plus C over B would not be A plus C over B plus B. When we have the same number on the bottom of both fractions, when we have the same denominator, when we have like fractions, we keep that denominator. We don't add the denominators together. We have a common denominator that allows us to add or subtract. We keep that common denominator as the denominator of the sum or of the difference. So A over B plus C over B, add across the top, A plus C, but keep it over just B, not B plus B. A over B minus C over B, subtract along the top, A minus C, but keep the B on the bottom. Don't do B minus B. That would be 0. We wouldn't even be able to do that. So add across the top or subtract across the top, whether we have plus or minus, and then keep the number on the bottom. The key is we're not allowed to take that step of adding or subtracting along the top unless we have like fractions, unless the same numbers on the bottom. So A, B, and C here, we are seeing that we have the same thing on the bottom of every fraction in A, of every fraction in B, and of every fraction in C. So we can add these. For A, I'd like you to think of pizza. Pizza is often cut into 8 pieces. Unless you're talking about your larger sizes, then you're getting into 10 or more pieces. But primarily, as long as you're not at a personal pan, you're talking about 8 pieces. Is this a lecture about pizza or is this a lecture about math? So 3/8, imagine that one person eats 3 out of the 8 slices. Plus 2/8, imagine that someone else eats 2 out of the 8 slices. How many slices have been eaten out of the total? Well, 5 out of 8. Fractions, when we add them, work like eating pizza. 3 slices plus 2 slices is 5 slices. It didn't change that there were 8 slices. The 8 stayed 8. We kept the number on the bottom that was the same, and we added along the top. 3 plus 2 is 5. B, 5 over 8x plus 1 over 8x. Keep what's on the bottom, keep the 8x on the bottom, but add along the top, 5 plus 1. 5 plus 1 is 6. We have 6 over 8x. We can simplify this. 6 is 2 times 3. 8 is 2 times 4. The 2's cancel. We're left with 3 over 4x. Why didn't we simplify in A, but we simplified in B? Well, A, there was nothing to simplify. 5 and 8 don't have any common factors other than 1. 6 and 8 did. That's why we simplify in B. And then in C, we have 3/8 plus 5/8 plus 4/8. We're adding 3 fractions. That doesn't change what we do. They're all 8 on the bottom, so we keep the 8 on the bottom, and we're allowed to add along the top. 3 plus 5 plus 4. That's 8 plus 4. That's 12/8. 12/8 can be reduced. 12/8 is 4 times 3 over 4 times 2. The 4's cancel. It's 3 over 2. And we can leave it as 3 over 2. Or we can divide and get 1 and 1/2. Or if we know we're going to go mixed number from 12 over 8, we can divide there, get 1 and 4/8, and the 4/8 reduces to 1/2. Either way, you're going to end up at 3/2 or 1.5 because we had to simplify. A here. Now we're subtracting. 8/9 minus 1/9. Well, imagine your pizza's cut into 9 slices. I know we're talking crazy now. And there's 8 of the 9 slices left, and then you come up and you take one of the 9 slices. How many of the 9 slices are left? 7 of the 9. There was 8 and you took one. There's 7 left out of 9. Keep the number on the bottom, keep the 9 on the bottom. That allows us to subtract along the top. 8 minus 1 is 7. 7/9. In B, 7/8 minus 5/8. We have 8 on the bottom of both fractions. We keep that 8 on the bottom. That allows us to subtract along the top. 7 minus 5 is 2. 2/8 is equal to 1/4. Divide top and bottom both by 2. Let's complicate things. Just like we had to know how to add and subtract when one or both of the numbers is negative, we need to know how to add or subtract when one or more of the fractions are negative. This doesn't change our fraction addition process. -11/8 plus 6/8. The number on the bottom is 8. We keep the 8 on the bottom. That allows us to add along the top. Be sure to collect your signs. -11 plus 6 is what we would have along the top. So we add -11 plus 6. That gets us -5. So -5 divided by +8, negative divided by positive is negative. So we have a negative overall fraction, -5/8. Let's look at a subtraction involving an x. This doesn't change what we do. In order to subtract these fractions, we see that there is a 4 on the bottom of both. We keep that 4 on the bottom. We subtract along the top. 3x minus 7, they are not like terms. We cannot simplify that any farther. So 3x minus 7 over 4 would be the answer. Don't start getting into +3 minus 7, it's -4, and -4 over 4, maybe -1 is the answer. Don't get into any of that. They're not like terms. We cannot combine them. The 3x and the -7 shall never interact. Perimeter. Recall that perimeter is the distance around. It's the sum of the sides. So if we had sides of 7/12 meter and 5/12 of a meter, We would add the sides. There's two sides that are 5/12ths. There are two sides that are 7/12ths. So 5/12ths plus 5/12ths plus 7/12ths plus 7/12ths. We're adding four fractions, but we're not overwhelmed. They all have 12 on the bottom, so our answer is going to have 12 on the bottom. And then we add along the top, 5 plus 5 plus 7 plus 7. That's 10 plus 14. That's 24 over 12. And hey, 24 over 12, that's 24 divided by 12. That's just 2. So the perimeter of this rectangle is 2 meters, not 2 meters squared. That is a mistake. I'm going to fix that real quick. Okay, just 2 meters. Why would it be wrong to say 2 meters squared? Well, because here we're adding meters. Meters plus meters is meters. Meters squared implies that we're finding the area, the stuff inside, what we get when we multiply meters times meters. Meters squared would be an area problem. Perimeter problem stays meters. A recipe calls for 1/3 of a cup of brown sugar and 2/3 of a cup of white sugar. How much total sugar is in the recipe? Well, the total sugar would be the brown sugar plus the white sugar. 1/3 plus 2/3. Keep the 3 on the bottom. Add along the top. 1 plus 2 is 3. So 1/3 plus 2/3 is 3/3. Just like 1x plus 2x is 3x. And then 3/3, anything over itself, anything divided by itself is 1. So the total amount of sugar in the recipe is 1 cup. Now, we know how to add and subtract fractions as long as they have the same number on the bottom, as long as they have a common denominator. But there are plenty of fractions out there that don't have the same denominator. So our first step towards being able to add or subtract those fractions is being able to find the least common denominator, the LCD, of a list of numbers. The first method is by using multiples of the largest number. I'm going to jump straight to the example to make sense of this process. The largest number is 12. Let's write the multiples of 12 until we find a number that's also a multiple of 9. 12 times 1 is 12. That's not a multiple of 9. 12 times 2 is 24. That's not a multiple of 9. 12 times 3 is 36. That is a multiple of 9. So 36 is the least common denominator of 9 and 12. So this is just brute force. We list out the multiples of the larger number until we come across one that's also a multiple of the smaller number. This could take a while in certain situations. It's not the ideal method for larger numbers. It's also not the ideal method for many numbers. Another method we have is to find the LCD using prime factorization. We'd write the prime factorization of each number, and then we'd circle the greatest number of times that factor occurs in any one factorization. The LCD is the product of the circle factors. Let's walk through this one. So 72. 72 breaks down to 2 times 2 times 2 times 3 times 3. Go ahead and make the factor tree. You'll see that. 60 breaks down to 2 times 2 times 3 times 5. Go ahead and make the factor tree. You'll see that. Well, we're going to circle the greatest number of prime factors found in either factorization. The greatest number of 2's is 2 times 2 times 2. The greatest number of 3's is 3 times 3. And the greatest number of 5's is just 5. We're comparing the 2 times 2 times 2 from the 72 to the 2 times 2 in the 60. 3 of them is greater than 2 of them. Same with the 3 times 3 in the 72 compared to the 3 in the 60. 2 of them is greater than 1 of them. So the LCD is the product of the boxed factors here. 2 times 2 times 2 times 3 times 3 times 5, which is 360. You can see that'd be pretty inconvenient if you were doing your multiples of 72. 72 is not a multiple of 60. 144 is not a multiple of 60. 72 times 3, not a multiple of 60. Keep going. Eventually you'd hit 360 and you'd go, hey, 360 is a multiple of 60. But this prime factorization method, this will get us an answer every time without having to go through potentially a pretty long list. And what if you're going through your list of multiples and you say that it's not a multiple when it actually is, and you miss the correct answer? This way you don't have to worry about that. So now let's see these numbers, these denominators in their fractions. So for 1/15, 5/18, and 53/54, we would be looking for the LCD, the least common denominator of the denominators 15, 18, and 54. So let's find the prime factorizations of 15, 18, and 54. Use your factor trees. 15 is 3 times 5. 18 is 2 times 3 times 3. 54 is 2 times 3 times 3 times 3. Our unique factors are 2, 3, and 5. So 2, 3, and 5 will make up the LCD. How many of each depends on what the most number of factors of each is. So for 2, we have 1, 2, and we have 1, 2. So that's just going to be 1, 2. For 3's, we have 1, 3, we have 2 3's, and we have 3 3's. The largest is going to be the 3 3's. And for the 5, there's only the single 5. So the single 5, the single 2, and the 3 3's are what make it into the LCD. Multiply all that out, and you get 270. List-wise, you would have to find the first number in common to the multiples list of 15, 18, and 54. So you would have to do 54 is not a multiple of 15 and 18. Then 54 times 2, 108. You'd go 108 is not a multiple of both 15 and 18. And you would keep going until you hit 270. And then when you hit 270, you would have to realize 270 is a multiple of both 15 and 18. It's going to take a long time to get there. And when you do get there, you may not recognize it. So this LCD method, using the prime factorizations, that's the way to go. We want the LCD of 3/5, 2 over x, and 7 over x cubed. So the LCD of 5x and x cubed. 5 is just 5. X is just x. X cubed is x times x times x. So the unique factors are 5 and x. The most number of times we have 5 as a factor is just this single 5. The most number of times we have x as a factor is this x times x times x. So that's the LCD, 5 times x times x times x, or 5x cubed. Before we move on, I want to get technical with you for a second. And we've been referring to the LCD of the fractions and the LCD of the numbers on the bottom, both as LCDs, least common denominator. Technically, the least common denominator of fractions are the least common multiple of the numbers on the bottom. So when we're looking for the LCD of these three fractions, we're actually looking for the least common multiple, the LCM of 5x and x cubed. But for simplicity's sake, we've just been calling everything an LCD, whether we're looking at a fraction or whether we're looking at a list of numbers. But there is a technical difference between the two. LCD is specifically for fractions. LCM, least common multiple, is what we're looking for when we're actually looking for the least common multiple of the list of numbers. So why? Why did we just do all that? Well, it's because to add or subtract unlike fractions, we would first have to write equivalent fractions with the LCM as the denominator. So to write an equivalent fraction, we multiply the top and the bottom by the same number. What number? Whatever number we need to get to the least common denominator. So if a over b is a fraction, we can multiply by c over c, multiply by c on the top, multiply by c on the bottom. We get the equivalent fraction ac over bc. So let's write an equivalent fraction with the indicated denominator. 3/4 equals how many 20ths? Well, ask yourself, what are we multiplying by? 4 times what is 20? Well, 4 times 5 is 20. So if we did 4 times 5 on the bottom, we would have to do 3 times 5 on the top. And 3 times 5 is 15. So 15 20ths would be an equivalent fraction with the denominator 20. Let's rewrite 4 as an equivalent fraction with 9 as a denominator. So first of all, 4 is 4 over 1. So we'd have 4 over 1 equals something over 9. How do we get from 1 to 9? We multiply by 9. If we multiply by 9 on the bottom, we have to multiply by 9 on the top because 9 over 9 makes 1, and 1 doesn't change it when we multiply. So 4 over 9 gives us 36. And of course, 4 times 9 gives us 36. And of course, the 1 times 9 gave us the 9. So the equivalent fraction with the indicated denominator, the equivalent fraction to 4 with the denominator 9 is 36 over 9. And we can see that's equivalent. 36 over 9 means 36 divided by 9, which is 4. So they are equal. Finally, let's take a look at 8 over 3x equals something over 24x. We want an equivalent fraction to 8 over 3x that has the denominator of 24x. Three x times what is 24x? Well, 3x times 8 would be 24x. So since we're multiplying by 8 on the bottom, we have to multiply by 8 on the top. 8 times 8 is 64. So the equivalent fraction is 64 over 24x. And you might say, hey, we could reduce that. We could have reduced all of these. But we don't want to because the directions said to write an equivalent fraction with the given denominator. It didn't say simplify the fraction. If we simplify, we're just going to end up right back where we started with 8 over 3x. The whole point of this is to almost unreduce because we're building up to getting the same denominator when we don't originally have it. And only then will we be able to add or subtract unlike fractions. That's it for this topic.